Ukrainian authorities say their forces targeted a Russian ammunition depot in the south of the country overnight, resulting in a massive explosion captured on social media. Well, it comes as the battle for the east of the country continues.
At exactly 10:18 a.m. on March 28, 2025, two HIMARS rockets launched toward their target at 2,300 miles per hour. Every millisecond counted. Senior Russian generals, monitoring air defense radar feeds in real time, watched as S-400 systems struggled to respond. They needed at least 60 seconds to intercept, but the rockets closed the distance in less than 5 minutes, leaving no margin for error. What made these rockets impossible to stop? In the aftermath, the Sudzha gas processing facility was left crippled, with damage estimated at $50 million. To understand why this remote site became the center of such a high-stakes operation, we need to examine its true strategic value. The Sudzha gas processing facility stood as a linchpin in Russia's energy and military infrastructure. Located in a remote sector of Kursk Oblast, it appeared on the surface to be an unremarkable industrial site. In reality, Sudzha's daily throughput of thousands of cubic meters of natural gas fed not only the civilian grid, but also logistics hubs, weapons storage depots, and manufacturing plants tied directly to the Russian war effort. Its uninterrupted operation sustained critical military supply lines and underpinned the functioning of industrial complexes, producing armaments and material. This integration turned Sudzha from a simple energy node into a vital artery for both the economy and the machinery of war. Neutralizing Sudzha was not a matter of disrupting routine energy production. Its output powered the logistical backbone that kept Russia's armed forces supplied and its factories running. A single disruption could cascade through supply chains, creating shortages that would ripple from the battlefield to industrial centers. For Russian planners, the facility's seamless connection to national pipelines and military logistics made it indispensable. The consequences of a successful strike extended well beyond the immediate loss of processed gas. It threatened to choke off resources essential to ongoing military operations and economic stability alike. The facility's position deep within Russian territory added another layer of complexity. While its location provided a sense of security, the reality was that Sudzha's defenses were tailored to protect against high-end threats. Russian military planners deployed a multi-layered air defense network specifically to shield this site. The first line of defense relied on S-400 early warning radar, capable of detecting targets at long range and tracking multiple objects simultaneously. When a threat was identified, medium-range 48 N6 interceptors were primed to engage incoming missiles at significant distances. Closer in, Panzer S-1 units provided short-range protection, designed to intercept any projectile that managed to slip through the initial layers. These overlapping systems created a formidable shield, reflecting Moscow's recognition of Sudzha's strategic importance. The sophistication of these defenses highlighted the challenge for any adversary considering an attack. The air defense network was not static. It was adaptive, with mobile units and radar systems constantly repositioned to respond to perceived threats. This made the prospect of a successful strike on Sudzha a complex operational problem. Any attempt to neutralize the facility required not just firepower, but the ability to penetrate or evade multiple defensive layers in rapid succession. Sudzha's significance was further underlined by its role in both civilian and military domains. Interruptions to its operations risked fuel shortages and reduced gas export capacity, but the more immediate impact fell on the military. The facility's output was routed to logistics hubs supporting frontline operations and to manufacturing sites producing weapon systems. Its loss would slow the movement of material, disrupt repair and resupply efforts, and undermine the broader war effort. In this way, Sudzha was more than a processing plant. It was a keystone in Russia's strategy for sustaining conflict. The decision to target Sudzha carried both tactical and symbolic weight. Disabling a facility so deeply embedded in the national infrastructure sent a message that even the most protected assets were vulnerable. For Russian leadership, the strike demonstrated a clear breach of the presumed safety afforded by geography and layered defences. For adversaries, it was proof that no node in the logistics chain was beyond reach. Overcoming these defences required a weapon system with unique capabilities. Planners needed a platform capable of launching precise, GPS-guided salvos, striking from unexpected angles, and executing rapid shoot-and-scoop manoeuvres to avoid counter-battery fire. The challenge was not simply to reach Sudzha, but to do so with the speed and accuracy necessary to defeat the S-400 network and its supporting systems. This operational problem set the stage for the deployment of a system designed to outmaneuver and outthink some of the most advanced air defenses in the world. How does a 16-ton truck-mounted rocket launcher consistently outmaneuver such formidable barriers? The answer lies in the unique capabilities of HIMARS. HIMARS, short for the M142 High Mobility Artillery Rocket System, represents a convergence of mobility, precision, and adaptability in modern artillery. The platform is mounted on a 6x6 truck chassis, weighing just 16 tons, and is engineered for rapid deployment. Its compact design enables it to traverse rough terrain, rural backroads, and even narrow urban streets with minimal logistical support. Unlike traditional towed or self-propelled artillery, HIMARS requires little setup time. Hydraulic stabilizers anchor the launcher during firing, and the crew keeps the engine running, ready to initiate rapid relocation within 90 seconds of discharge. This capability to reposition quickly after firing is critical for survivability, especially when facing adversaries equipped with advanced counter-battery radars and precision-guided munitions. The operational core of HIMARS is the Universal Fire Control System, UFCS, which integrates GPS positioning, real-time weather data, and encrypted targeting coordinates into a single interface. This system receives targeting information via secure satellite communications, processes environmental and ballistic variables, and calculates the optimal launch solution for the mission at hand. The entire launch sequence is automated. Once the crew verifies the data, a single button press initiates the firing process. The UFCS determines trajectory, launch angle, and flight timing, eliminating manual guesswork and minimizing human error. This level of automation ensures that the system can deliver precision strikes in compressed timeframes, even under pressure. Preparation for a strike is methodical. The crew selects a firing position that balances concealment with firing range, deploys the stabilizers, and awaits the final targeting package. The UFCS incorporates not only the target's coordinates, but also atmospheric pressure, wind speed, temperature, and elevation changes between the launcher and target. These factors are computed almost instantaneously, allowing the crew to maintain a low profile and move out immediately after launch. Central to the HIMARS's effectiveness are the Guided Multiple Launch Rocket System, GMLRS, munitions. Each GMLRS rocket carries a 200-pound warhead and is equipped with both a GPS receiver and an inertial navigation system for redundancy. This dual guidance allows for terminal corrections, enabling the rocket to strike within 15 meters of its designated target, even at ranges approaching 70 kilometers. For the Sudzha operation, the crew loaded 2 GMLRS rockets, each programmed with a unique trajectory and arrival sequence. The UFCS coordinated their flight paths to ensure both rockets would impact simultaneously at separate points, maximizing destructive effect and complicating enemy interception efforts. This time-on-target sequencing is a deliberate tactic, forcing air defense systems to attempt multiple intercepts within a split second. a task that often exceeds their real-time response capabilities. The sophistication of the GMLRS extends beyond guidance. Each rocket's flight path is calculated to take advantage of terrain masking, using the contours of the landscape to reduce exposure to enemy radar. The rockets are programmed to fly at varying altitudes and approach angles, making it difficult for air defense sensors to track and engage both simultaneously. Should one guidance system encounter jamming or electronic interference, the inertial navigation backup ensures the rocket remains on course. Executing such a strike against a facility like Sudzha is not without risk. Russian air defenses, including the S-400 and Pantsir systems, are designed to detect, track, and intercept incoming munitions at various ranges. The margin for error is slim. A delay in launch timing, a miscalculation in trajectory, or a lapse in crew coordination could expose the launcher to immediate retaliation or allow the target to survive unscathed. The HIMARS crew must account for radar coverage, potential electronic countermeasures, and the likelihood of rapid enemy response. Every element, from the initial targeting to the final launch sequence, is designed to compress the window of vulnerability and maximize the probability of mission success. The decision to employ HIMARS for this mission was not based on chance. Its proven record in delivering precision strikes, combined with the flexibility to adapt to evolving battlefield conditions, made it the logical choice. The system's modularity allows for rapid reconfiguration to meet different operational needs, whether engaging hardened bunkers, enemy artillery, or high-value infrastructure targets. In this context, HIMARS function not merely as a weapon, but as a strategic tool, capable of shaping the operational environment and imposing costs on adversaries with speed and precision. As the firing sequence concluded and the rockets ignited, the crew's work shifted from offense to survival. The launcher was already on the move, disappearing into the landscape before enemy radars could triangulate its position. But the real test was now underway. With two 200-pound warheads racing towards Sudzha at over 2,300 miles per hour, the outcome would depend on a combination of engineering, tactical acumen, and the unforgiving physics of high-speed flight. As the rockets left the launcher, the science behind their flight took over. This was where strategy met engineering, the main topic at hand. The lead GMLRS rocket climbed rapidly to 45,000 feet, reaching speeds of 2,300 miles per hour as it arced toward its target. At this altitude, its GPS receiver locked onto multiple satellites, constantly updating its position and comparing it to the Sudzha facility's programmed coordinates. The trailing rocket followed a lower trajectory, its path calculated to arrive within milliseconds of the first. The two flight profiles were not accidental. They were designed to converge on the target from different angles, maximizing the chance of overwhelming any defense and ensuring simultaneous impact. During flight, each rocket's guidance system operated with redundancy and precision. The combination of GPS and inertial navigation allowed for continuous course corrections. If Russian forces attempted to jam satellite signals, the inertial system maintained accurate tracking by measuring velocity, position, and altitude. In the terminal phase, guidance updates occurred up to 50 times per second, allowing the rockets to compensate for atmospheric changes and any last-minute variables. This level of adjustment ensured that, even as the rockets descended from high altitude, their trajectories remained tightly aligned with the intended impact points. The approach to the Sudzha facility relied on more than just speed and guidance. Both rockets used terrain masking, following flight paths that kept them below radar coverage for much of their journey. Natural features in the landscape, including hills and forests, were used to minimize the time each rocket spent exposed to Russian radar. The lead rocket approached from the northwest, while the second came in from the northeast, forcing Russian operators to track two separate vectors. This tactic not only reduced detection time, but also complicated the process of predicting the rocket's final destinations. Radar evasion was further enhanced by the rocket's design. Their surfaces and overall shape reduced radar cross-section, making them appear on screens as targets no larger than a large bird. Combined with their high speed and low altitude flight profiles, this presented a significant challenge for Russian radar operators. The S-400 system, deployed to protect high-value sites like Sudzha, required at least 60 seconds to detect, track, and fire an interceptor. In this case, the system had only 45 seconds after initial detection, a window too short to coordinate a firing solution. Even the shorter-range Panzer defense systems depended on accurate tracking data from the S-400. Without that, their chances of intercepting the rockets were minimal. As the rockets closed in, their final approach was marked by precision. 30 seconds before impact, proximity fuses activated. These sensors measured altitude in real time, recalculating the optimal detonation point multiple times per second. The warheads would detonate at the precise height needed to maximize damage to the facility's critical infrastructure. Even in these final moments, the guidance systems continued to make fine adjustments, ensuring the rockets stayed on course despite any last-minute defensive measures. The Russian air defense network, built on the premise that deep-lying assets were out of reach, was forced to confront a new reality. The combination of terrain masking, resilient navigation, and compressed response timelines left little opportunity for effective countermeasures. The staggered trajectories and near-simultaneous arrival of the rockets further reduced any chance of interception. In the seconds before impact, the Sudzha facility's fate was already sealed. With the rockets now entering the final meters of their flight, all that remained was the execution of their precisely programmed mission. The science and strategy that had guided them from launch to target would soon be measured by the effects on the ground. The explosion that followed at Sudzha was the result of deliberate engineering and precise timing. The first HIMARS rocket, carrying a 200-pound high-explosive warhead, struck the main processing unit with surgical accuracy. Traveling at more than 2,000 miles per hour, the warhead delivered its kinetic energy directly into the reinforced concrete shell. Upon impact, the PBXN-109 explosive inside the warhead detonated at a velocity of 26,000 feet per second, collapsing the copper liner into a focused jet. This shaped charge jet, moving at hypersonic speeds, penetrated up to 3 feet of reinforced concrete or 2 feet of hardened steel. The jet bored through the outer defenses and into the heart of the gas processing system, targeting compressors that maintained natural gas at 75 times atmospheric pressure. The result was an immediate breach of the plant's most critical containment, releasing vast quantities of pressurized natural gas into the facility's interior. Exactly 15 seconds later, the second HIMARS rocket struck the central control building. This warhead was programmed with a 0.5-second fuse delay, enabling it to pierce the structure before detonating deep inside the SCADA control room. The explosion unleashed a fragmentation sleeve containing over 180,000 preformed steel fragments, shredding control systems and emergency equipment. The delayed detonation was calculated to ensure the warhead exploded at the point of maximum vulnerability, destroying the computerized infrastructure that could have activated emergency shutdown procedures. Magnesium incendiary components, burning at 3,100 degrees Celsius, ignited everything flammable, from wiring to control panels, guaranteeing that the facility's operational nerve center was completely neutralized. The sequence of impacts was designed to produce a cascading catastrophe. The initial breach by the first rocket allowed compressed natural gas to escape and mix with atmospheric oxygen, forming a highly volatile fuel-air mixture. The second rocket's explosion provided multiple ignition sources, damaged electrical systems, sparking control panels, and severed power lines, all of which could ignite the dispersed gas. Within moments, the fuel-air mixture reached the optimal ratio for combustion, filling the facility and its surrounding infrastructure with an invisible explosive cloud. When ignition occurred, the result was a detonation rather than a simple fire. The flame front propagated at supersonic speed, producing a shockwave of immense force. The power of the explosion was immediately apparent. The resulting blast generated a fireball visible for miles and a pressure wave that tore through steel pipes, shattered windows kilometers away, and destroyed structural supports throughout the complex. Seismic monitoring stations located more than 100 kilometers from Sudzha registered a 2.1 magnitude event on the RTER scale, evidence of the energy released in the blast, equivalent to the detonation of 50 tons of TNT. At the epicenter, temperatures soared above 1,800 degrees Celsius within the first minute, melting steel and igniting secondary fires throughout the facility. The intense heat caused the underground storage tanks, filled with reserves of natural gas, to rupture in rapid succession. Each failure added new fuel to the inferno, ensuring that the destruction was both total and irreversible. The warhead design was central to this outcome. Each GMLRS rocket was engineered not only for penetration, but also to maximize internal damage and prevent recovery. The shape charge overcame hardened barriers, while the delayed fuse allowed detonation at the most vulnerable point inside the target. The fragmentation sleeve, with its 180,000 steel fragments, extended the destructive radius, obliterating equipment and personnel alike. Magnesium incendiaries ignited residual gas and flammable materials, making any attempt at containment or repair impossible. These features combined to ensure that Sudzha was not simply damaged, it was rendered permanently inoperative. In less than 5 minutes, the Sudzha facility was reduced to ruins. Decades of investment and sophisticated engineering were undone by 2 rockets weighing less than 700 pounds in total. The main processing unit was destroyed, the control center obliterated, and the auxiliary systems left inoperable. Damage assessments put the loss at $50 million, but the true cost extended far beyond infrastructure. The fire burned for hours, preventing emergency response and leaving the site inaccessible. With every vital system destroyed, the prospect of reconstruction became remote. The psychological impact was as profound as the physical devastation. The Sudzha strike demonstrated that even the most heavily defended sites deep within national borders could be neutralized with precision-guided munitions. The efficiency of the attack, 2 rockets, near-simultaneous impacts, and total destruction served as a stark illustration of the evolving nature of modern warfare. For Russia, the event exposed a vulnerability that could not be ignored. For military strategists and observers worldwide, it was a clear signal that the balance of power and the rules of engagement were shifting. The consequences of the Sudzha explosion extended far beyond the immediate aftermath. As the fires burned and the reality of the destruction set in, it became clear that this was not just the loss of a facility. It was a demonstration of how precision and technology are redefining the landscape of conflict, an unmistakable message that would shape the thinking of military planners and policymakers in conflicts to come. The HIMARS strike on the Sudzha gas facility resulted in the site being rendered completely inoperable, with equipment losses estimated at $50 million. This outcome demonstrated the precision and destructive capability of GMLRS rockets against a target protected by advanced air defenses. The failure of the S-400 and Panzer S-1 systems to intercept the incoming missiles revealed that even critical infrastructure deep within Russian territory remains vulnerable to modern precision-guided artillery. This operation sent a clear strategic message. High-value assets are no longer beyond reach. Let us know in the comments. How do you think precision artillery like HIMARS is changing the future of warfare?